This video is about a parallel computer program. It's called pSIN, pSIN, which stands for parallel seismic interferometry for large N data. So it's a parallel software. It's a parallel code that allows you to carry out ambient noise, seismic ambient noise cross correlations very efficiently. So uh, so I'll talk about how we can actually build the code and how we can actually run this code, and I'll explain some of the important considerations when using this particular software for ambient noise cross correlation calculations. To build this code, it's not too complicated. This is an example makefile. Basically, you have to sort of put all these lines into a makefile and then use the GNU make utility, MAKE make utility to actually just compile and build this program. It's got just a one source code. It's pSIN.cpp. That's a one C++ code, right? And then it's got just one target. So after you have finished compiling it, you will get one executable, binary executable, which is called pSIN, right? And because it's written using the message passing library, message passing interface library, MPI. So when you compile it, when you compile this source code, you have to use MPI C++, right? So whatever version of message passing interface should be sort of compatible with this code. You can just use this utility MPI C++ to compile this this binary, right? But when you actually compiling it, you have to link some external libraries, and the external library we'll have to use is called FFTW. It's a Fourier transform library. It's being used very widely, and it's quite efficient. It's actually very efficient, and because the cross correlation implemented in this code is carried out in the Fourier domain, in the frequency domain, by doing conjugate multiplication. So you have to convert seismic signals, noise signals, into the frequency domain, and we're using FFTW to do that for transform. And in order to actually link to the FFTW libraries, you have to sort of define these two environment variables, INC, that's for including the headers of the library, and then lib, that's the library itself. And on my machine, the INC is defined to be -I. That's for the directory. That's the standard kind of flag for including header files, declarations of variables, that kind of thing. Header files. Those things usually go into the header files. So you need to sort of put the FFTW include directory beneath behind the -I, right? And on my machine, the included directory is this particular directory. You have to. It's a Linux operating system. So this is a sort of the absolute path to a particular directory that's called include, right? And inside of this directory, inside of this include directory, it has lots of header files that belongs to the FFTW library. And then you have to sort of do the same thing for the lib, right? So the front part is exactly the same as the include, except that the subdirectory has changed to from include to lib. And then don't forget to -L FFTW3F. You have to be really careful about this F here. So FFTW3 actually has FFTW3 is sort of the latest version of FFTW. So it's the version is like 3 point something. So it's called FFTW3 now. FFTW3 has lots of different versions. The default version is for double precision, right? But in my code, pSIN.cpp, I'm using the single precision, the floating point version. It's slightly faster than the double precision version, and the accuracy is actually sufficient for most of the ambient noise cross correlation applications, and we have actually carried out lots of experiments to test which precision is actually sufficient, and we found that floating point precision, just a single precision is actually sufficient for us to retrieve robust ambient noise Green's functions by cross-correlating and stacking ambient noise recordings. So we are using this FFTW3F library, which is just for single precision floating point Fourier transforms. And this library is actually not built by default, I believe. So you have to look into the configuration files when you actually try to build FFTW. The FFTW website actually gives a very detailed explanation about how to actually build the different libraries in this FFTW package, right? So you can just look into it, and when you configure the build, you have to sort of enable explicitly the the target for a floating point, a single precision floating point FFTW3 library. Otherwise, it's not going to generate it. It's not going to generate a single precision library for you. So you have to sort of enable it during the configuration stage when you install FFTW on your particular machine. And once you actually have that, you just do mpi c++ with the including directory. -o gives you the target, and then the source code, and then followed by the library. That's basically the library that you define here. The INC is defined here, right? And basically that's how you actually compile this code. It's not too complicated. Later on, in later versions of this code, will add more functionalities into this code. Maybe the build process will become more complicated. But for now, the first version of this code is just a one source code, and it's relatively easy to build. Now let's look at how we can run this code, right? And it's a parallel program, so usually you submit your binary executable to a job management system. So here's you need to write a job script, right? In this case, my job management system is called a Slurm, S-L-U-R-M. It's called Slurm, and you have to write this kind of CSH script, TCSH script. But your job management system could be different from mine, so you could just maybe you don't have a job management system, right? If that's the case, you just use mpi run, get rid of .lsf, and then the rest of the parameters is exactly the same. But if you have a job management system, you need to write a job script. This kind of job script basically requests for resources, the number of processes and the amount of time that you need to use those resources. So here's an example job spec script for the Slurm job management system, right? So you have to request, it's basically a TCSH script, right? It's a shell script, right? The first line is it's telling you that, and then you need to request the queue number. You need to give it an account number because it's going to charge to the resources that you're going to use for this particular run is gonna charge it to this particular account, to my account. This is my account, right? And then the amount of time you are requesting for this particular example, it's using 1 hour 30 minutes. And then the most important thing is probably the number of core, the number of MPI processes that you are actually requesting for this particular run. In this case, I'm requesting 2,112 processes, and you want to run 16 MPI processes per node, right? This is tailored to my cluster. On your cluster, this might not be the case, right? If every node of your cluster actually has just, for example, 8 processes, then this might be 8 here, right? The thing is that on this particular cluster, every node actually has 16 cores. So I want every core to have 1 MPI process running on it. So that's why I'm requesting ptile equals to 16, so that every core is on one node is being utilized. So basically you are requesting the number of nodes you are requesting is this number divided by 16, right? And so it's 2,112 divided by 16. Which should be 32, or 132. It's 132 nodes basically, right? So I'm requesting by doing these 2 lines, I'm basically requesting for 132 nodes, right? And then I'm utilizing all 16 cores on each of the node. So that gives me 2,112 MPI processes, right? And then the job name, then the output file, and the error output file, right? And then we need to sort of run the executable. Basically, we are just submitting our binary executable, parallel binary executable pSIN to this particular MPI run This is a very special version of MPI run. It's for the Slurm job management system. In your case, it could be MPI exec, right, or S run, or AP run, or whatever sort of command that's kind of tailored to your particular job management system, right? This is our binary executable, para binary executable, and then all these kind of options are given to this binary executable. So let me just go through each of the parameters and explain what's actually their meaning. So you see two numbers here, 66 and 32. So 66 is the virtual topology, the virtual process topology row number. And then 32 is the two-dimensional virtual process topology column number. So this is a process row number. This is actually a process column number. So here we actually requested 2,112 MPI processes, right? And these many processes are being organized into a two-dimensional virtual topology. It's basically just like a matrix. And this matrix has 66 rows and 32 columns. So it's basically a two-dimensional process grid. And this two-dimensional process grid has 66 rows, 66 process rows, and 32 process columns. And if you multiply these two together, you're going to get 2,112 back. So if you don't believe me, just do 66 multiply 32. That's exactly 2,112. The reason that it's being called a virtual topology is because this kind of organization of MPI processes happens only inside of the pSIN code. It's not sort of imposing any kind of topology to the cluster that you are actually using. So the job management system is just going to allocate 2,112 processes for you. How these 2,112 processes are organized on the cluster is completely up to the job management system. But inside the pSIN code, you can actually look at this kind of or organize all these 2,112 processes into this kind of two-dimensional virtual grid. Right? It has no physical association to the hardware or MPI processes whatsoever. It's just a virtual topology that allows us to deal with the MPI communication patterns more efficiently. I'll explain this two-dimensional virtual topology in a later slide. But for now, these two numbers is for the process row number and the process column number. And how we can actually select these two numbers depends upon the problem at hand and also the organization, and also the cluster, right? The cluster we're actually using. So I'll explain how we can actually select these two parameters in a little bit. And then followed by a text file. It's a name of the text file basically. For this particular example, this bin lst, this particular text file is located in the current directory, so there's no path name in front of it. But if it's not located in the current directory, then you by current directory I mean the directory where you actually store this particular job script, this text file. That's the current directory, right? If this particular text file is stored in the same directory as the text file of this job script, then I don't need to append any path in front of it, right? But for now, it's in my current directory, so I don't need to sort of give it a complete path. But if it's not in the current directory, you can put the complete absolute path of that particular text file in front of the file name, and then the code will also work, right? So what I'm telling you is that this is basically just the name of a text file. And then the next number is the sampling interval, the sampling rate of your noise recording. So here 500 just means that for my ambient noise recording, I have 500 samples per second. So the sampling interval is just it's just 0.002 seconds, right? So every consecutive two samples. Every neighboring two samples has a sampling interval of 0.002 seconds. So 500 is just the sampling rate of my noise recording. So basically, I'm telling the code that all the noise recording is going to have like 500 samples per second. This is actually universal. This number must be the same for all the noise recordings using your array. For now, the pSIN encoder cannot deal with uneven sampling rate across the array. So if you have like two stations that have different sampling interval, then pSIN encoder cannot be used. You have to resample it to the same sampling interval before you actually use pSIN encoder. So pSIN encoder actually assumes every station in your array has exactly the same sampling rate. And for this particular example, the sampling rate is just 500, right? So if different stations in your array has different sampling rate, you need to sort of interpolate them or decimate them into to exactly the same sampling rate before you use pSIN encoder for computing the cross correlations and ambient noise Green's function. And then that's the next number. The next number is what? So when you do the ambient noise Green's function calculations or ambient noise cross correlation and stacking, you have to actually truncate the entire recording of each station into pieces, into lots of small pieces, and you're actually cross correlating those small pieces together, right? You have to segment the entire time recording, which could be like several days or several months, into segments, and this number basically specifies how many points you're going to use for every segment. So here it's 65536, and this number has to be a power of 2. A power of 2. So this is basically 2 to the 18th power or 2 to the 16th power. This number is 2 to the 16th power, right? So for this particular example, every receiver actually has a recording of 4 days. Basically, it's a continuous recording of the noise for 4 days, right? For 4 days, right? At a sampling rate of 500 samples per second. So I'm actually truncating. pSIN code is actually going to truncate the entire recording, the entire time series of 4 days, 4 days of recording into lots of small segments, and each segment is going to have this many samples, right? And this number has to be a power of 2, and you can, in later versions of the pSIN code, we're going to allow numbers that's not exactly a power of 2, but for now it must be a power of 2 for now. And then it's followed by 2 numbers. These 2 numbers are used for normalizations in time domain and also for frequency domain, right? So in time domain, it's gonna do a moving window average using the maximum amplitude within that moving window, right? So every sample in that moving window is going to be normalized or divided by the maximum amplitude of that of the noise within that short moving window. And the width of the moving window is specified here. It's 0.2 seconds, so it has a unit of second. It's a 0.2 seconds. Right? It's for time domain normalization. Right? So the reason for doing time domain normalization is just to get rid of some kind of sort of non-stationary signals like an earthquake or like some kind of some sort of abnormal activities like a truck being driving by or some kind of human noise that's generated by culture activities, that kind of thing. So it's some kind of transient signal, right? But what we are interested in is actually the ambient noise. So we need to get rid of or normalize away those kind of transient signal, like an earthquake or something. So you need to do this kind of time domain normalization. And this point 2 is the width of the moving window. And how do you actually select this number, right? This number is being selected based on uh, a classic paper by Benson et al. In 2007 about the classical ambient noise cross-correlation analysis. It's half of the period, half of the dominant period that you're actually interested in, or half of the dominant period that your instrument is actually sensitive to. It's selected based on the dominant period of the noise recording, right? And then this number is sort of frequency domain normalization. In frequency domain, we're also doing this kind of moving average, moving window average, or moving window normalization thing. But the um, so the amplitude spectrum, the amplitude of spectrum in the frequency domain is gonna be divided by the sort of the maximum within the maximum amplitude within a window, and this 100 is in terms of sampling points in frequency domain, right? So it's gonna do a 100 point moving window average or moving window normalization in the frequency domain. So it's basically taking just the 100 points every time, and then find out what's actually the maximum amplitude within, the average amplitude within that 100 point window, and then divide every point within the amplitude of the amplitude of every sample within that window divided by that number, right? So it's a frequency domain normalization. And then the last parameter is a path name. It's actually a name to a directory, basically. This directory is going to be used for storing the output generated by pSIN, basically the stacked cross correlations, right? And you have to give it either an absolute path or relative path, right? This is a Linux operating system, so you have to give it a path name, and that's it. That's how you can actually run this code. So now let's look at bin list first. What this file actually looks like. Right? This file looks like that, like this kind of thing. It's bin list. It's a text file. I'm actually just doing a head bin list. I'm just looking at the first 10 lines in this particular text file, right? And each line in this particular file is just the absolute path and file name to the complete recording. To the complete recording of just to the complete ambient noise recording of one receiver or one station in your array. So here it's just by looking at the file name, you can just tell what this file actually is, right? It's an array 3, right? And then station 1, and then array 3, station 2, right? Your file name doesn't have to be organized like that with underscores, that kind of. It can be any file name. It doesn't really matter. It doesn't really matter what the file name actually is. All you have to do is to list. Every file name for your entire dataset, and one file name is just for one receiver, right? So the entire recording of one receiver in your array is basically just one file, and you have to list all those files in the particular order that you would like it to be. Right? You have to be careful about the row number of a particular station and the station ID. pSIN doesn't actually recognize any of those station IDs. It doesn't really do that. pSIN just recognizes the row number. So it's gonna treat the file on the first row of this particular bin list file as the first station, and it's gonna treat the second row, the file on the second row, as the second station, and it's gonna treat the file on the last row as the last station, and it's gonna do all the calculations, all the cross correlations for you. right? So when you actually look at the output file, it's not going to be exactly, or if your row number does not corresponding to your station number, then the output file is going to just be the cross correlations of so suppose here I'm actually having 1 and 2. That's sort of the row number actually corresponds to the station number, right? But that doesn't have to be the case. Suppose I move this line. I move the 10 station to the second line, right? So STA1 and then followed by STA10 and then followed by STA2, 3, 4, 5, like that kind of thing, right? pSIN is not gonna sort of recognize the second row is actually station 10 for you. It doesn't actually do that. It just recognizes the first row is the first station, and then the second row is the second station. So it's just not gonna do the cross correlation between 1 and 10, right? And then output that cross correlation as the ambient noise gradients function for 1 and 2, right? Because station 10 is actually on row 2, right? So in the output file, when pSIN actually writes out the output file, it's gonna tell you that this particular cross correlation is between row 1 and row 2. It's not for station 1 and station 2, right? Because row 1 and row 2 is actually station 1 and station 10, right? So depending upon how you actually organize this particular text file, the output is gonna have different meanings. So it might be important to realize that, right? So if you want the pSIN output to actually correspond to a station index, then it might be a good idea to organize the file so that the row number corresponds to the station number, right? So the next question is how each of these binary files are organized, right? What's actually the content of each of the binary files, right? So here is actually a piece of code for reading. The pSIN actually uses this piece of code to read each of the binary file. So you can sort of see what's actually the organization of this code, right? So it's gonna read 1, 2, 3, 4, 5. It's gonna read 5 numbers before it actually reads the noise recording itself, right? And these 5 numbers are the header of each of the noise recording. So T0 is a double precision. T0 is a double precision. You see, it's a double, define a double here. It's a double precision floating point number. And this number represents the absolute time of the first sampling point. The first sample, right? So it's a double. It's not a time. It's not exactly a format of time, right? When you talk about time, it's usually year, months, that kind of thing, right? Year, month, day, hour, minute, second, that kind of thing. But this is not. This is just a double precision floating point number. It actually represents the second number, the number of seconds with respect to a particular reference time. So if you actually have a reference time that's being used by your entire array, and that reference time is, for example, 1970, year 1970, January 1st, 0th hour, 0th minute, 0th second, right? If that's your reference time for your entire array, then this T0 is just the time difference between the first sample of this particular file with respect to that particular reference time in terms of seconds, how many seconds it has elapsed, right? It's just that. It's seconds. It's in terms of seconds, right? With respect to a particular reference time that is kind of a exactly same reference time for the entire array, right? You have to make sure that this T0 is referenced to a common reference time. The reference time can be anything, right? But it has to be the same for all the data in the entire array. Right? It has to be the same for all the data in the entire array, and T0 must be referenced to that common reference time. And then XC and YC are both doubles. They are both doubles, right? And they actually represent the coordinates of the receiver. These two numbers are not exactly used, by pSIN, but pSIN is going to use T0. It's not going to use XC and YC, but these two numbers are for the coordinates of the receiver, right? So if you are using UTM, Universal Transverse Mercator, that kind of coordinate system, then XC could be easting in terms of meters, YC could be northing in terms of meters, right? Could be, but it doesn't really matter for pSIN. It's just two numbers representing the coordinates of the receiver. And then array ID, right? Array ID and receiver ID. Again, these two numbers are not used by pSIN at all. These two numbers are not used by pSIN at the current stage. They are not using these two numbers, but both of them are actually floats. They are floating point numbers. Floats. It's not double. It's a single precision floating point number. Array ID and the receiver ID. Right. It's just used for identifying data. Right. Identifying the particular array. So that's the 5 header numbers, header fields. Right. You can change these lines also. You don't really have to sort of use this particular format in your binary data, right? If your binary data has a different format, has different number of headers, for example, then you can just change these lines in the pSIN code. You can easily find those lines in the pSIN code. But this line is actually necessary. pSIN actually uses T0, so you must have a reference time. You must have a T0. That's the absolute time of your first sample with respect to a common reference time, and then it starts to read the data. So here it starts to read the data, and the data is stored in a floating point array, a single precision floating point array that's called S. You can sort of see it's defined as a float star here, right? And the number of samples, big NS, has been determined previously. So it's big NS is determined based on the length of the binary file, right? So pSIN is going to look at the length, the size, how many bytes the entire data actually has, right? So it's going to read the rest of the data in single precision. So it's a single precision data, right? So if your data is actually in double precision, it's recorded in double precision, then you might want to convert it into single precision first before using pSIN, right? Or if you have the if you want to read the source code, you can sort of change it, right? Change it to double here. But you may also need to sort of change lots of other places in the code to change it to double. But it's quite difficult, right? In later versions of the code, we might consider introducing double precision, right? But for now, floating point single precision is like enough for our calculations, so we did not actually do double here, right? But if you want to sort of use double, it could be a feature that's going to be in future versions of the pSIN code, right? Now let's look at how we can actually select the correct the appropriate process row numbers and process column numbers, which is actually how we can select these two numbers here, right? So in order to understand that, we need to understand basically how the data is going to be partitioned in the memory of the entire cluster, right? So every cluster, most of the clusters these days are actually distributed memory. So it means that each process or each node has its own memory, right? And a different node has no direct access to the memory of other nodes, right? So node 1 doesn't have direct access to the memory of node 2, right? So if node 1 wants some data from node 2, then it has to go through the network, right? That's why we are using message passing interface. The message passing interface is just a way for one node to retrieve the data that's residing on the memory of another node. Basically, it's a data transportation process, right? So how we gonna partition the noise data of the entire array on all the different nodes of your entire MPI process array, right? So each node, each receiver or each station is represented as a row here. So here we have like 3 rows, right? So noise recordings of 3 stations, right? Noise recording of 3 stations. They all just a random noise, right? Ambient noise. pSIN is gonna cut them into pieces, right? Each noise recording is gonna be cut into lots of small segments, right? All of them. The noise recordings of all receivers are going to be cut into lots of small pieces. And each piece or each segment is going to have this many points. And pSIN is going to do 0 padding if the length of each of the station is actually if the length of the noise recordings from different receivers are different, then pSIN is going to do 0 padding. Right? It's going to pad zeros in the front, pad zeros in the back to make sure that the noise recordings of all receivers of the entire array is exactly the same length, has exactly the same length, right? So and then it's gonna cut them into lots of small pieces, right? And each piece is gonna have that many this many samples, right? Of course, you can change this number to a different number, right? Based on your data set, right? It doesn't have to be this number. You can change it to any number, as long as it's a power of 2, right? But pSIN is gonna cut those into like lots of small pieces, right? And then you have different receivers, right? Right. For each receiver, you have lots of different segments, right? And then you have lots of receivers in the entire array. So how are you gonna organize all those noise data so that you can minimize the kind of communication or transportation of data among all your MPI processes, right? And that's sort of a tricky question you have to sort of address. You don't want to sort of keep the noise recordings of one entire receiver in the memory of one node, because if that's the case, when you do the cross correlation, you have to transmit or communicate the entire recordings of one receiver from other receivers, from other processes, right? That's gonna be quite a huge amount of communication cost, right? And you don't want to store the entire the same time segment from all receivers of your array into just the node of one process, right? Because if that's the case, when you actually do the stacking process, when you do the noise cross correlation, you're gonna stack, right? It's a cross correlation followed by stacking. Stacking is basically summation. In MPI programming, it's a reduction process, right? If you don't want, if you partition the entire data according to time segments, then when you do the stacking, it's going to introduce lots of communication cost, right? So a better choice is actually to group those data into like blocks, and each block has a small number of time segments for a small number of receivers, right? So what you're going to do is that a better way for dealing with this kind of process is to group those segments from different receivers into smaller groups, right? And each process is going to just hold a subset of those groups, right? So basically, we're cutting the entire noise recordings into like multiple segments, right? So this row is basically this row here, right? But we're cutting them into like 1, 2, 3, 4 pieces, right? And then each process is going to have like so this is process, this is one of those processes, right? And this process is going to have like 2 pieces, 2 segments of the first trace, right? And then this is another process, right? And it's going to hold 2 pieces or 2 segments of the first trace here, right? And then the first process is also going to hold the first 2 pieces of the second trace here, right? The second trace is also cut into like multiple pieces, right? Multiple segments, right? And the first process is gonna hold like two segments, and then the second process is holding like two segments of the second row, right? And then this is like the third process, right? The third process is gonna hold this row is basically corresponding to the third row here, right? You're cutting it into like four pieces, and then the third process is gonna hold like two pieces of that, right? The fourth process is gonna hold two pieces of that. This is for the third row, right? And then for the fourth stage, for the fourth station, for the fourth row, you're gonna do the same thing, right? So this is one process, this is another process, this is a third process, a fourth process, right? So you can sort of see if you organize the noise into this kind of chunks, then you are introducing a two-dimensional topology to the total number of processes also. So each of those blue boxes is actually the memory, of one process, right? And those memory are actually kind of independent of each other. So on one process, the memory is like independent of the memory of another process, right? So you cannot assume those the memory space for these two processes are actually on the same node. You cannot assume that because you are actually using MPI to do the message passing, right? So that gives us a virtual topology, a virtual two-dimensional topology for organizing all the processes, all the MPI processes in our process array. So that's the process row number, right? And then that's the process column number. For this particular example, it's two row, two column, right? Two row, two columns. Right? So what might be a good choice for the process row number and process column numbers, right? So the rule of thumb is that you wanna sort of keep small number of receivers on each process, but you want to keep more segments on each process. So here we have like two receivers and two segments on one process, right? In practice, you may want to sort of keep like a few, 5 to 6 receivers, right? But as many segments as you can onto one process. So you basically have to have understanding about how large the memory is for each of the core that you are actually using, right? And then determine the size of each segment, right? Determine the size of each noise segment, right? And then you have a rough understanding about how many segments you can hold in total, right? And then what you want to do is to keep as many segments as possible onto one process, right? The reason is that the communication among rows, among different columns of the same row, is a reduction operation, is a reduction MPI process communication, right? When you do the stacking, you have to sort of stack the different time segments together, right? And that kind of stacking is a communication among different columns of the same row, right? Reduction doesn't go through this thing, right? Reduction doesn't involve communication for different rows of the same column. It doesn't do that. It just involves communication among different columns of the same row. And this reduction operation is not very scalable. It's not very scalable for current hardware, for most of the clusters, for most of the MPI clusters these days, right? But the cross-correlation process, if you want to compute, this allows you to compute the cross-correlation between station 1 and station 2 on one process, station 3 and station 4 on the other process, right? But if you want to compute correlation between station 1 and station 3, then it's going to involve a communication across different rows but on the same column, right? So you basically have to move this data to here. And this communication cost is actually very scalable. It's implemented using MPI send receive routine, and it's actually quite scalable, right? So it's okay if you actually partition the rows or partition the stations into many different process rows, right? but it's not a good idea to separate the time segments into lots of different columns. So in order to come up with a realistic estimate of the process row number and process column number, you need to know what's actually the memory space for each of the core and the size of each of the segment. And then you can experiment. You can experiment and see what's going to be the configuration that allows you to achieve a minimal processing time, right? The minimal amount of time for calculation, right? And the reason that this kind of partitioning is important is because the communication cost for reduction and send and receive reduction across different columns of the same row, and the send and receive for different rows of the same column is actually quite different, right? So one possibility is to sort of carry out multiple experiments and find out what's actually the configuration, what's actually the optimal setup for your cluster, right? It's hardware dependent, certainly. It's certainly a hardware dependent parameter, right? But the two-dimensional topology is the two-dimensional virtual topology is a way for you to actually adapt, or a way to adjust, adapt to that kind of communication cost, right? So for this particular data set, bin list, I actually have like 396 lines, 396 rows in this bin list file, right? I have this many stations in my array, about 400, 396 stations in this particular data set. And then I'm actually partition it into like 66 rows, 32 columns. So 396 divided by 66. So this is 6. So each process is going to hold 6 receivers, right? But it's not holding the entire recording of 6 receivers, right? It's just holding a number of time segments, of those 6 receivers. So 6. This is the number of samples of each time segment, right? And so I actually have like each receiver actually records for like 4 days. 4 days. So pSIN, when pSIN is actually running, it's gonna report how many segments. If you give it like 32 process columns, right? If you 4 days of recording, that's like 4 times 24 hours times 36. So that's this many seconds, right? This many seconds times 500. So that's this many samples, right? This many samples, 65536 samples. So for my 4-day recording, if I truncate the entire recording into pieces with this many samples per piece, then I'm gonna have like 2,637 segments, right? And this many segments is sort of being divided by 32, because my process column number is 32, right? So for each of the each processor is gonna have like about 82 time segments, right? If I use 32 as my process column number. So each process is gonna contain the noise data of 6 receivers and 32 time segments, right? And this number is actually printed during the run of pSIN, and you can sort of check it out, see if that's sort of exactly the same as your estimate, right? Don't forget, pSIN is gonna pad zeros for you, right? So all the noise data is gonna be zero padded to exactly the same length, right? Now let's look at the output files generated by pSIN. So when you actually did the run, this is actually the directory for storing the output files. So all the output files generated by by pSIN are going to be stored under this particular directory. And if you do an ls, in that directory, you're going to see lots of files that's named like that, right? Basically, it's actually two groups of files, two sets of output files. One is named like pSIN.idx followed by 4 numbers, and the other one is called pSIN.ou followed by 4 numbers, right? So these, that's the four numbers actually is the row index and the column index of each of the process. Don't forget, we're actually using a two-dimensional topology, virtual topology, for organizing all the MPI processes, right? So each of the MPI process is going to have an ID that's consisting of row number and a column number, right? Process row number, process column number. So basically, that's process row number, and then that's process column number, right? So depending upon what's actually the row number and column number you specify here, you're going to see different numbers, right? So here I have like a row number is 66, right? So the first two numbers, the first two numbers is going to go from 0 to 65, right? That's 66 rows, right? And then here I have like a 32, right? 32 as the process column number. So the next two numbers is just going from 0 to like a 31, right? From 0 to 31. That's for the sort of the process column number. So basically that's process ID, but this time it's a two-dimensional process ID, right? So you have like a row number and a row number here, and then followed by column number, right? So that's a process ID. And then you have this thing and also this thing, right? The stacked cross correlation actually is stored inside of these files. So those .ou files actually are the stacked cross correlations, but they are actually stored in binary format. They are stored in binary format, right? Don't forget about it. And this is also stored in binary format, but these are integers. These are integers. It's also in binary format, but they are in integers. So the stuff that's being stored inside of these files are the cross correlation indices. So if you're actually doing a cross correlation between 1 and 2, row 1 and row 2, then if this process actually corresponds to 2606, right? If that's the process, right? And then the first two numbers in pSIN is just going to be 1 and 2, right? So if this is a receiver 3 and 4, right, the first number in the corresponding process ID is just going to be in that .idx file is just going to be 3 and 4, right? Two integers. So these files, these .idx files, are actually storing the row index, not exactly the station index, right? Do you guys remember? At this point, we were actually talking about the difference between row index and the station index, right? So if you actually organize the stations according to rows, then row index and station index is sort of the same, right? But if it's not, then what's being written into this particular file is actually row index in that bin list file, right? It's going to tell you the corresponding .ou file are generated for which station pair or which row pair, basically, right? So you're going to have a pSIN.ou 2606 file, right? And this particular file, this .idx file, is basically telling you the row indexes of each of the cross correlation inside of the .ou file, right? So if the first cross correlation or stacked cross Green's function in that .ou file is for row 10 and 20, then the first two integers inside of this particular binary file is just 10, 20, right? So these files can all be you can read those files into MATLAB just like ordinary binary files. There's no header information. There's no decorations or metadata stored in those binary files. They are just flat one-dimensional binary files, right? So you want to read those index files first to find out the corresponding .ou files are actually storing how many cross correlations first, right? And then you want to read the .ou file, the corresponding .ou file, right? How many cross correlations is stored in the .ou file is just the length of, or the total number of integers in this file divided by 2, right? Because each cross correlation takes 2 rows, right? It's row 1 with cross correlating with row 2, that kind of thing. Row 10 cross correlating with row 20, right? So every cross correlation involves 2 rows, right? So you just read the number of integers in the IDX file divided by 2, then you get the number of cross correlations in the corresponding .ou file, right? Once you know the number of cross correlations in the .ou file, you can just read that .ou file into MATLAB as a flat floating point binary file, right? And in a later version, I will provide better sort of management of the output files, right? How do you actually manage those output files in a more sensible way, right? For now, it's just organized like that.